All right, good morning, everyone. Okay, the next chapter in the textbook is one on spectroscopy. I'm going to skip over that and we'll come back to it. That's also going to be covered in lab when we go remote, but I'll cover it in lecture as well. I'm going to skip over that for now, and we're going to move on to aldehydes and ketones. Okay, can everyone hear and see okay? Can you hear and see okay?
Yes.
Yeah.
Okay, good, thanks. All right. All right, the aldehydes and ketone functional groups contain this subunit called the carbonyl, the CO double bond. The CO double bond is not itself a functional group. It's a component of several other functional groups, including aldehydes and ketones, which we'll talk about in this chapter. Carboxylic acids, which will be considered in chapter 13, also contain the carbonyl. Acid halides, anhydrides, esters, and amides. And then we may or may not talk about enolate anions. That will depend on if time allows. Okay, if the carbonyl is bonded directly to a hydrogen, then we have an aldehyde. The simplest aldehyde is formaldehyde. Its IUPAC name is methanal. Okay, we take methane, which is one carbon, we drop the E, and then the suffix is al for aldehyde. Okay, don't confuse that with methanol, which is an alcohol. Right, then this is acetaldehyde in the middle, or ethanal in the IUPAC. Propanone, okay, this time the suffix is -one. We have a ketone. There's no hydrogens directly bonded to the carbonyl carbon, just two carbons. This is much more commonly known as acetone. Right, the carbonyl group consists of an sp2 hybridized carbon and an sp2 hybridized oxygen. Okay, both of these have a trigonal planar geometry. There is a sigma bond between the carbon and oxygen as a result of overlap of these two sp2 orbitals. And then there's a pi bond. Okay, there were 3 p orbitals, but we only used 2 for hybridization, so there's one unhybridized, which is perpendicular to the trigonal planar electron distribution, and these form a pi bond. Right, for the oxygen, the other sp2 orbitals contain lone pairs. Right, to name aldehydes or ketones, again, we look at the longest carbon chain that contains the principal functional group, that contains the carbonyl group. And as I mentioned, for an aldehyde, we change the suffix from E to al. And for a ketone, it's -one. Okay, for an unsaturated aldehyde or ketone, we'll show the carbon-carbon double bond by changing the infix from AN to EN, the location of the suffix then determines the numbering pattern. Okay, we'll see some I'll show you some examples of that. All right, for a cyclic molecule in which CHO, that is the aldehyde group, is bonded to the ring, we'll add the suffix carbaldehyde. All right, so here are some examples. Okay, this is up in the left-hand corner. This is 3-methylbutanal. Okay, the aldehyde has to be on number 1, and so we don't need a locant number. Okay, it's understood that that's where the aldehyde is, and it takes priority, so the methyl is on 3. Okay, here is 2-propenal. Okay, the 2 indicates the position of the double bond. The ene indicates that we have a double bond. And we drop the E after ENE because the next letter is a vowel. Right, acrolein is a compound that's produced from the breakdown of fat. And this has a sharp, very sharp odor. And in fact, it smells like grilling of steak, okay? And as a matter of fact, when you grill meat, especially when it's well done, this is given off, and it has a pungent, acrid odor. Okay, this is one that has 2 double bonds and an aldehyde. So this is 2E, 3,7-dimethyl, 2,6-octadienal. Okay, the 2 and the 6 indicate the positions of the double bonds, diene, 2 double bonds. Okay, this is a fragrant essential oil that is produced from geraniums, geraniol, sorry. Okay, here we have cyclopentane carbaldehyde. Okay, there is no such thing as cyclopentanal. Right, cyclopentanal would have the aldehyde as part of the ring, and that gives this carbon 5 bonds, so that's it. That's not possible. To call this one cyclopentanal is also incorrect because cyclopentanal implies there's only 5 carbons, but you can see that there's 6, and so the carbaldehyde takes care of the additional carbon. One thing that is different about cyclic and an acyclic aldehyde is that for the acyclic, okay, this is pentanal, and the aldehyde is position number 1. For the cyclic compound, okay, this position on the ring is position number 1. Right, so this would be 1-methyl cyclopentane carbaldehyde. Right, the aldehyde group takes priority over alcohols. Okay, if an alcohol is the principal group, then the suffix is -al. But in this case, since the aldehyde takes priority, not only is it on number 1, but the alcohol being a substituent is a hydroxy. So this is trans 4-hydroxycyclohexane carbaldehyde. Right down at the bottom, we have some ketones. Okay, on the previous slide, we had acetone. This is dihydroxyacetone, or in the IUPAC, it would be 1,3-dihydroxy propanone. Okay, since a ketone is between two carbon atoms, it doesn't have to be at the end of a chain. And so for an acyclic ketone, we do have to specify the location of the carbonyl. So this is 5-methyl-3-hexanone. Okay, the 3 is the position of the ketone. Right, if we have a cyclic ketone and the ketone is the dominant functional group, in this case, it's understood that the ketone is on carbon number 1. Okay, so this is 2-methyl-cyclohexanone. Right, this is commonly called acetophenone, and the IUPAC would be 1-phenylethanone. Okay, but nobody calls it that. Commercially, it's acetophenone. All right, and then this is benzophenone. Benzophenone is also commonly called diphenylketone. Acetophenone is sometimes called methylphenylketone. Okay, so here is a chart of the priorities. Okay, the sulfhydryl or the thiol group down here at the bottom, if it is the dominant functional group, then the suffix is thiol. If it's not, then we use the prefix mercapto. Okay, so this is 2-mercaptoethanol. The alcohol takes priority. The amino group is also lower priority than an alcohol. If the amino group is the dominant group, then it's an amine. If it's not, then it's an amino substituent. So this is 2-amino 1-propanol. Okay, the alcohol takes precedence. Okay, a ketone takes precedence over an alcohol. Okay, so down here with these last two, where the alcohol was the dominant functional group, the ending is -ol. But when the alcohol is not the dominant group, then it's a hydroxy. Okay, so this is 4-hydroxy-2-butanone. Okay, and the ketone also gets a lower number. Right, what if we have an aldehyde and a ketone in the same compound? Okay, by IUPAC rules, the aldehyde takes precedence. Okay, so this is butanal, and then the ketone substituent is an oxo. Okay, not an oxy, but an oxo. So this is 3-oxobutanal. You don't see this next one very often, but if you have an aldehyde and a carboxylic acid, then the aldehyde is also an oxo. Okay, so this is 3-oxopropanoic acid. Okay, and then carboxylic acids are way up at the top. Okay, we'll talk more about naming carboxylic acids when we come to that chapter. Okay, many aldehydes are known by common names. For aldehydes, the common name is derived from the common name of the corresponding carboxylic acid. Right, so the simplest carboxylic acid is called formic acid. The simplest aldehyde is formaldehyde. Okay, this is acetaldehyde. Note the similarity to acetic acid. And then ketones, as I alluded to in the previous slide, sometimes these are named by identifying the two alkyl or aryl groups on either side of the carbonyl. So this is methyl ethyl ketone, or MEK. MEK is an important solvent like acetone. Organic compounds tend to be, some of them tend to be more soluble in methyl ethyl ketone. Methyl ethyl ketone, though, is less soluble in water than acetone. This is diethyl ketone. And then this is dicyclohexyl ketone. Okay, in terms of physical properties, okay, these are the result of the high polarity of the carbonyl group. Oxygen is more electronegative than carbon, okay, 3.5 versus 2.5, and therefore the carbonyl group is polar covalent. Okay, you can see that, okay, not only is there a dipole moment, but if we look at the resonance structures, there's a minor contributor that actually has a full positive charge on the carbon and a negative charge on the oxygen. Okay, in the electron paramagnetic map, this is for acetone. Okay, the oxygen is electron dense. The carbon, though, is color-coded in blue, so it's electron poor, or partially positive. Okay, the dominant intermolecular interaction between aldehydes and ketones is dipole-dipole interactions. As a result, these compounds have higher boiling points and are more soluble in water than nonpolar compounds with comparable molecular weight. For liquid aldehydes and ketones, there are weak intermolecular attractions between the carbon dipole of one molecule and the oxygen dipole of another molecule. Hydrogen bonding is not possible between aldehydes or ketone molecules. And as a result, aldehydes and ketones have lower boiling points than alcohols or carboxylic acids, which are compounds of which hydrogen bonding between molecules is possible. Okay, so these compounds all have very similar molecular weights. Here we have diethyl ether, or ethyl ether. Its boiling point is 34. Pentane, 36 Celsius. Right, butanal now is 76. Okay, and 2-butanone, okay, same molecular weight, very similar boiling point. Okay, again, dipole-dipole interactions. 1-butanol has a considerably higher boiling point, 117, and then propanoic acid has a considerably higher boiling point. Okay, the carboxylic acid has one site that can act as a hydrogen bond donor and acceptor, and another site that can act as an acceptor. So you have strong hydrogen bonding in carboxylic acids. Okay, let's look at water solubility. All right, methanol or formaldehyde is a gas at room temperature. Its boiling point is -21 Celsius. It is infinitely soluble in water. There is a disclaimer here. Okay, actually what happens when you dissolve formaldehyde in water is there's actually a chemical reaction that occurs between it and water, and it forms this, what is called a hydrate or a gem diol. Okay, at equilibrium, 99% of the molecules are in this form. In the case of ethanol or acetaldehyde, about 57% are converted to the corresponding hydrate. Right, propanol is 16% soluble in water. Okay, so you can see that as the number of carbons increases, the solubility goes down. Okay, hexanol with 6 carbons just has a slight solubility in water. Okay, acetone. Okay, you've probably washed your glassware in the lab with acetone. It is infinitely soluble in water. Methyl ethyl ketone is less soluble, and 3-pentanone or diethyl ketone is only 5% soluble in water. Okay, backing up for just a minute. Okay, as the aldehyde, as the carbon chain on the aldehyde gets longer, there's less and less of this hydrate formed at equilibrium. Okay, but for formaldehyde, that constitutes 99% of its form in water. Right, the most common reaction theme of a carbonyl group is reaction of an electrophile and nucleophile to form a new covalent bond. Okay, since the carbon has a partial positive charge, it attracts nucleophiles or electron pair donors. And when these nucleophiles attack, there's an intermediate that has this tetrahedral shape. Okay, so we form a covalent bond. We break this pi bond. We push a pair of electrons up onto the oxygen. Okay, so here we had 2 lone pairs. Now we have 3 and a negative charge. Right, addition of carbon nucleophiles is one of the most important types of nucleophilic additions to a carbonyl group because the new carbon-carbon bond is formed in the process. So that means we can build just about whatever carbon skeleton that we want. Okay, we're going to study the addition of carbon nucleophiles called Grignard reagents. Okay, these were named after Victor Grignard, who was awarded the Nobel Prize in Chemistry in 1912 for their discovery and application to organic synthesis. Okay, that was over 100 years ago, and Grignard reagents are still very widely used today. Grignard reagents have the general formula RMGX. R is an alkyl or aryl group. It could be a benzene ring, for example. And X is a halogen. Not fluorine, but the halogen is chlorine, bromine, or iodine. Grignard reagents are prepared by adding an alkyl or aryl halide to a suspension of magnesium metal in diethyl ether. Okay, turns out the solvent actually is very important here. Okay, and this has to be absolutely dry. Okay, so here we have bromobutane reacting with magnesium metal in ether. And notice what happens is the magnesium will end up inserting itself between the carbon and the bromine. So we get butyl magnesium bromide. This also works for aromatic compounds. We can produce phenyl magnesium bromide from bromobenzene. Okay, if we look at the difference in electronegativity between carbon and magnesium, okay, it's 1.2. The carbon-magnesium bond is polar covalent. This time, we have reversed the polarity at the carbon. Okay, so carbon now has a partial negative. Magnesium has a partial positive. Okay, back here in 1-bromobutane, the carbon had a partial positive charge. Okay, that's how we could do SN2 reactions, where a nucleophile attacks this carbon, kicks out the bromide. Okay, but now we've reversed the polarity. Now carbon is more electronegative than magnesium. Okay, so a Grignard reagent is like a carbanion. A carbanion is an anion in which carbon has an unshared pair of electrons and bears a negative charge. A carbanion is a good nucleophile and adds readily to the carbonyl group of aldehydes or ketones. Okay, so we can think of this Grignard as being like a carbanion. Okay, the carbon, there's a high electron density at the carbon, so it behaves like a carbanion. Okay, this first reaction is usually one that you don't want to happen. Okay, when you're doing a Grignard reaction in the laboratory, you want to be very careful to exclude water. Okay, it turns out that the Grignard reagent is a very strong base. And if water is present, carbon immediately grabs a proton, we get ethane, and the reaction's over. Okay, we can see that this is definitely product favored. Ethane has a pKa of 51, whereas water is 15.7. So water is a much, much stronger acid than ethane. Okay, so this goes all the way to product, goes very quickly. Okay, so we have to exclude any compounds that have an OH, NH, or SH group because they're going to react with the Grignard by proton transfer. Okay, turns out we also need to exclude terminal alkynes. Okay, they have a pKa of about 25. Right. This just shows one example of that, and that is we have to also avoid alcohols. Okay, ethyl magnesium iodide. Okay, that is like a ethyl anion. It will immediately grab this proton. We get ethane, and that's it. Alcohols typically have pKs about 16 to 18. Remember, water's 15.7. So most alcohols are a little bit weaker than water as acids, but we still have to avoid them when using Grignard reagents. Right, here, however, is a useful reaction. And since this chapter is about aldehydes and ketones, we can use Grignard reagents to react with aldehydes or ketones to form alcohols. Okay, so again, this is still done in ether. You need the ether to stabilize the Grignard reagent. Okay, so carbon has a partial negative charge, so carbon, this pair of electrons, will attack the partial positive carbon of the carbonyl, push a pair of electrons up onto the oxygen. Okay, and then we have to wait until this reaction is finished before we add dilute acid. Okay, and this may be something like 3 molar HCl. Okay, this last step is simply an acid-base reaction where the alkoxide grabs a proton from hydronium and we get an alcohol. If we're using formaldehyde, we'll end up with a primary alcohol, 1 carbon longer than what we started with. Okay, even though we could use water here, the reason that we don't is that we'll form a precipitate of magnesium hydroxide, and that makes the workup, the isolation, a little more difficult. Okay, this way, by using dilute acid, we keep the magnesium dissolved. Okay, if we start with some other aldehyde, okay, here the example is acetaldehyde or ethanal, we'll get a secondary alcohol. Okay, so this attacks the carbonyl. We form a bond between the first carbon of ethane and the cyclohexane ring. And then when this reaction is complete, then we add dilute acid to the reaction mixture. This picks up a proton, we get our secondary alcohol. Okay, so this would be 1-cyclohexyl ethanol. Right, when a Grignard reagent reacts with a ketone, okay, we end up with a tertiary alcohol. Okay, this is exact same mechanism. The Grignard, the carbon bonded to the magnesium, attacks. Okay, notice we don't do anything with magnesium or the bromine. It just falls off. So don't worry about drawing any arrows from it or to it. Okay, and that gives us a tertiary alcohol. This would be 2-phenyl-2-propanol. Okay, propane is the longest chain containing the alcohol, 2-phenyl-2-propanol. Okay, in this problem, we're going to work backwards. And there are actually 3 different ways that we could make this using a Grignard synthesis. Right, the strategy here is to find the CO bond, not the double bond. If we locate the CO bond and we break the next carbon-carbon bond. Okay. If we break it here, right, the part without the oxygen, we make that the Grignard. Okay. Arbitrarily, I chose bromine. We could also do this with chlorine or iodine. All right, the part with the oxygen, we take away the hydrogen, and we make this a double bond. Okay, so there's a Grignard, there's your ketone starting material. All right, we could also break it here. Okay, so that means that we would have a methyl Grignard. And then we would make this a double bond, take away the H, make this a double bond. So phenylethyl ketone would be your other starting material. Okay, and then the third way would be to break it, and we locate the CO bond, we break the next carbon-carbon bond, so we break it at the ethyl. So we would start with acetophenone or methyl phenylketone and ethyl magnesium bromide. Okay, so here we have addition of an alcohol. A hemiacetal is defined as a molecule that contains both an alcohol and an ether group that are bonded to the same carbon. Okay, so here we have an ethyl ether and an alcohol on the same carbon. Okay, so this is the result of the reaction of acetone with ethanol with either a small amount of acid or base catalyst. Okay, in the vast majority of cases, hemiacetals are minor components of an equilibrium mixture. Okay, so this first reaction, there's going to be very little of this hemiacetal. It's going to be almost all starting materials. An exception, though, is where we can form an intramolecular hemiacetal that forms a 5 or 6 membered ring. Okay, in this case, the ring is actually favored. Okay, here's an example. This is 4-hydroxypentanal. Okay, the lone pair on the alcohol attacks the carbonyl. We have some proton transfers that take place, and that closes up the ring. Okay, and this is the major component at equilibrium. The ring is still continuously opening and closing, but again, this is the main component. Okay, so most hemiacetals are not stable. Okay, if we have 2 molecules of an alcohol or a diol that adds to an aldehyde or ketone, then we get an acetal. Acetal is defined as a molecule with 2 ether groups on the same carbon. In contrast to hemiacetals, which are mostly not stable, acetals are actually stable. Okay, so how do you form an acetal? All right. So first we form a hemiacetal. Okay, where, let me back up just a minute. Okay, and under acid conditions, what happens here is the carbonyl picks up a proton, the lone pair on the oxygen of the alcohol then attacks the carbonyl, and then water removes that extra proton, removes this proton. Okay, so once we get that hemiacetal, the alcohol group then gets protonated again. We have this oxonium ion. Water leaves. We have a resonance stabilized cation. You can see that the plus charge is delocalized between the carbon and the oxygen. Okay, so this is an especially stable carbocation. Right, then another alcohol attacks. We form another protonated acetal, oxonium ion, and then a base or water removes this extra proton, and we end up with the acetal. Okay, although acetals are stable, the formation of acetals, it's an equilibrium reaction at every step. Every step is reversible. So we need to choose our experimental conditions such that we remove the water as it is formed. Okay, otherwise it would simply go back to starting material. That helps to drive the reaction to the right and to acetal formation. By manipulating the equilibrium using a large excess of water, an acetal can be converted back to its original aldehyde or ketone. Right, so here we have a couple of questions. How would we form an acetal from these? Okay, here we have a diol, and okay, we went through the mechanism. There is a simple shortcut to predict the product here. Okay, so we have cyclohexanone and ethylene glycol, or 1,2-ethylene-diol. Okay, if we draw the two molecules in this arrangement, okay, we're removing water. Take out an O and two H's like this. Right, and this is the acetal that we would get. Okay, in this case, it's a cyclic acetal. Okay, two ethers on the same carbon. Okay, similarly, the second problem. If we line up our two starting materials like this, we'll remove water. And that gives us this acetal. Okay, and then the last thing I want to mention, just very briefly, we'll look at this in more detail next time, and that is acetals make really good protecting groups for example, for Grignard reactions and a lot of other reactions. Okay, if this is the compound that we wanted, okay, it would not work to make a Grignard from this 4-bromobutanol and then attack, because we have another carbonyl which would interfere. Okay, but if we make the cyclic acetal first, then make the Grignard, okay, then this works. And then once the addition is complete, we use dilute acid to remove the acetal, and we can make the desired compound. Okay, so I'm going to end there, and I will see you on Monday.